Imagine a world where AI doesn't just predict the next word in a sentence, but understands the deeper structure of language the way humans do. Not through brute force memorization, but by modeling the actual logical relationships between ideas, concepts, and meanings. That's the promise of a new frontier in artificial intelligence, reasoning-aware language models. For years, large language models have dazzled us with their ability to generate fluent text, answer questions, and even write code. But beneath the surface, they're fundamentally pattern-matching machines. They don't understand, they simulate understanding. They predict what comes next based on statistical correlations in massive datasets. And that's a problem when you need real reasoning, when you need logic, consistency, and the ability to follow chains of inference. But recent breakthroughs in AI research are beginning to change that. We're moving beyond pure prediction toward models that can reason, not just mimic it. Let's break this down. At the core of this shift is a new architecture, neural-symbolic integration. This isn't just a buzzword, it's a fundamental rethinking of how AI processes information. Traditional neural networks excel at learning from data, but they struggle with symbolic logic. Things like if A, then B, or not all X or Y. On the other hand, symbolic AI systems are great at logic, but they're brittle and require hand-coded rules. The fusion of the two, neural-symbolic systems, creates something powerful, models that learn from data and reason with formal logic. Take the case of Neuro-Symbolic Concept Learner, NSCL. This model doesn't just classify images. It parses visual scenes using symbolic representations, objects, attributes, spatial relationships, then uses neural networks to learn how to interpret those symbols from raw pixels. When asked, is the red ball to the left of the green triangle, it doesn't guess. It decomposes the image into symbolic components, applies logical rules, and arrives at a correct answer with high confidence. But the real leap comes when we move from static reasoning to dynamic multi-step inference. Consider models like logic-enhanced transformers or reasoning transformers. These aren't just regular transformers with a logic layer tacked on. They're designed with internal mechanisms that simulate reasoning steps. How? By introducing reasoning modules, specialized subnetworks that perform logical operations, entailment, contradiction, negation, and inference chaining. These modules are trained not just on language, but on formal logic datasets, such as the SNLI, Stanford Natural Language Inference, and Fever, fact extraction and verification benchmarks. For example, given the premise, all dogs are mammals. Fido is a dog. A standard language model might correctly infer Fido is a mammal, but it's not guaranteed. It might hallucinate or fail under slight rephrasing. A reasoning-aware model, however, uses a dedicated inference module to chain the logical steps. From all dogs are mammals, universal quantification, to Fido is a dog, specific instance, to therefore Fido is a mammal, modus ponens. It doesn't rely on pattern matching, it executes the logic. And here's where it gets technical. These models often use differentiable logic. That means the logical operations are implemented in a way that's compatible with gradient descent. The model learns not just what to conclude, but how to reason, by adjusting the weights of its inference rules through backpropagation. This is a game changer. Because now, instead of being trained on millions of examples, a model can learn to reason from far fewer examples, sometimes even just one. That's few-shot reasoning. It's not just efficient, it's robust. The model generalizes better because it's not memorizing surface patterns, it's learning underlying principles. But the most exciting development: self-generated reasoning traces. Some models now don't just spit out answers, they think out loud. When presented with a complex question, they generate intermediate reasoning steps. First, I know that X implies Y. Second, since Z is true and Y implies W, then W must be true. This is called chain of thought prompting, but now it's being learned, not prompted. In models like DeepSeek R1, Gemini 1.5, or OpenAI's O1, the reasoning process isn't an afterthought. It's baked into the architecture. These models have been trained to produce coherent, step-by-step explanations that can be verified independently. And when you evaluate them not just on final answers, but on the correctness of the reasoning path, their performance skyrockets. This isn't just about better accuracy. It's about trustworthiness. When an AI can explain how it reached a conclusion, we can audit it. We can debug it. We can verify that it didn't arrive at a correct answer by accident. And the implications go far beyond chatbots and Q&A systems. In scientific discovery, reasoning-aware models can help generate hypotheses, validate experimental designs, and even uncover hidden relationships in data. In medicine, they can analyze patient histories and treatment protocols using logical consistency checks, flagging contradictions or gaps in reasoning. In legal reasoning, they can trace the logic of precedents and predict outcomes based on structured argumentation. But let's be honest, this isn't magic. These models still have limitations. They struggle with open-world reasoning, where not all information is known. They can be misled by ambiguous language or adversarial phrasing. And while they simulate reasoning, they don't experience it. They don't have consciousness. They don't understand in the human sense. But that's not the point. The point is, we're no longer just building models that talk like humans. We're building models that think like them, step by step, rule by rule, logic by logic. So what's next? The future lies in hybrid architectures that combine neural learning with symbolic reasoning, formal verification, and even mathematical proof systems. Imagine an AI that can not only answer questions but prove theorems, debug code by tracing logical errors, or design new algorithms with provable correctness. This isn't science fiction. It's happening now. And as we push deeper into this new era of reasoning-aware AI, one thing becomes clear. The next frontier in artificial intelligence isn't bigger models. It's smarter models, models that don't just predict but reason. Because if AI is going to solve real-world problems, complex, ambiguous, high-stakes ones, it won't be through more data or more parameters. It will be through deeper understanding. And that's not just a technical upgrade. It's a transformation. The future of AI isn't just about talking. It's about thinking. And we're finally building systems that can do both, better than ever before.